accepted.
I want one of those for every time I walk into a room. It'd be awesome, just like, here's James. So hi, thanks for coming. I appreciate it's sort of quite late in the day in Devoxx. Have we had a good Devoxx Poland this year? It's like being in Scandinavia, blimey. Good, I've had a brilliant time. I've been here many times now. I always love coming to the city. I love this conference. So I thank the organisers for having me back. My name is James Lewis. I work for a software consultancy called ThoughtWorks. We build bespoke software for large organisations, small organisations, and so on. And I've been there about 17 years, which is quite a while. I've been consulting for 17 years. I've been, I guess, writing code, crimping network cables for nearly 30 years. And this talk in some ways is about how I've come to understand what we do, like how we go about doing what we do as software developers or people who work in knowledge work. And so I've got a little demo to show you at the end, which is trying to put into software form my understanding of the domain model of what we do, so writing code, building software and things. But before we get there, I'd like to sort of take a bit of a journey through some of our history over the last sort of 10 years in terms of software engineering, the practices, the principles, the techniques we use, and some of the tools as well, because I think it's often important to try and take a step back and understand that a lot of the stuff we take for granted today literally didn't exist 10 years ago, which is kind of interesting. So there's part of this talk is about sort of history, part of it is about the current state of the art, and then part of the talk at the end is towards what that has taught me over the last sort of nearly 30 years about what we do and the importance of certain theories in what we do. Let me turn this on. But first, I'd like to put up a disclaimer, because I do have some stuff about declarative AI in here. So I'd like to point out that no large language model played a part in writing this talk. As of today, I mean, next time you see it, I could have replaced the whole thing, probably, with generated content, but I haven't. Next time all bets are off. So, life moves pretty fast. If you don't stop and look around once in a while, you could miss it. I'm very lucky at working at ThoughtWorks. I'm part of our Global Technology Advisory Board. That's the group that works with our CTO as her advisors. And we're pretty big these days. We're about nearly 13,000 people globally these days. And as part of that work with Rebecca, Dr. Parsons, my boss, we put together something called the ThoughtWorks Technology Radar. And I've been involved in that for the last 10 years. And one thing that's been fascinating for me is watching how quickly things move, watching how these new technologies appear and suddenly become massively adopted, and how many new technologies are appearing all the time. So to give you an example of how fast things are moving, every 6 months we get together to produce the ThoughtWorks Technology Radar. And there's about 20 people from around the world, from the different countries in which we've got offices, all turn up with items to talk about. And we tend to have I'll normally take about 30 or so new things every 6 months. Our Indian colleagues also bring about 30 things, but they'll have had over like 400 things suggested to talk about. And every 6 months, as a group, we talk through about 300 new items, new pieces of technology or techniques, tools, platforms, or languages. 300 new things every 6 months. That's pretty insane, right, in terms of how quickly things are moving. And things are only getting faster, actually. But just as a sort of reminder, some of these might be surprising. They were surprising to me. I looked back over when things started to appear on our technology radar over the past decade or more. Now, Android first appeared back in 2010. I mean, Android is only that old, right? That's pretty crazy. Git and Mercurial, so distributed version control systems, are only about a decade old. I'm sure we've got people in the room who remember SVN, going back further, CVS, and going back further, SCSS, and yes. But I mean, Git has sort of taken over the world, right? It's at the heart of everything, of all of our software development processes, more or less. But it's only that old. AWS. Oh, there. I'll go back. AWS again, only about 2011. ThoughtWorks, we were very early adopters of AWS. I'll come to why I think AWS is super important in a minute, because it relates to how work works. But this is when AWS first started to go mainstream. Back in 2011, I was one of the first 4 AWS trainers in the world, because Amazon didn't want to do it themselves, didn't want to provide training. So we said, hey, this is really cool tech. Maybe we could do some training for you. So they said, yeah, that's fine. So we developed a training course together, and that was the first AWS training. That was back in 2011, and again, like, that has completely changed the world of work, how we work. Who'd have thought AWS was a thing? This is actually a slide from the original training course. These were this is what they had at the time and when they were starting to be introduced. So 2010, they had Oracle, for the first time. And there we are, proudly as partners, our old logo. But who'd have thought AWS would have been a thing, right? I mean, there's this interesting thing with recently we've adopted platform engineering as a thing. Now, the interesting thing about AWS is, why is AWS so important? And yes, there's lots of interesting technologies we can use in AWS, but for me, the interesting thing is it inverted the equation wherein we don't need to ask people for stuff anymore, right? Back in the day, I remember in a project for a big telecom company. It was a 6-month project, and we asked their IT department, can we get a developer environment? And they said, yeah, that'll be 9 months. Like 9 months waiting for a new environment, or environment for us to even to develop on, to run our CI server on. Now, AWS completely changed that, right? Because we get access to these environments straight away. Essentially, we don't have to ask people to do stuff for us anymore. And that's a super important part of what makes us go faster, right? Our ability to do stuff on our own without having to put work into other people's queues. And I'll come to that in a minute. But AWS was the first, the first huge development that enabled then continuous delivery to take over the world later on, I think. And that's why AWS is the thing. It's not because it's scaling and auto-scaling and all this kind of stuff. I don't think. I think it's because it made the ops team get out of our way as developers and be able to get stuff done. So that's AWS. Continuous Delivery, the book was published shortly after. Jez Humble and Dave Farley, both thought workers. And again, AWS made those patterns more interesting, more available and easily implementable. Microservices then came just after that. 2012, first time it appeared on the radar. I can put my hand up and say sorry for that. Microservices back in the day, this is from a talk I did in 2011, actually in the city, where I talked about these as the sort of foundation for microservices. Had this thing about rewrite rather than maintain, etc., etc., etc. I should point out here another disclaimer. None of it was my idea. I just stole it from loads of other people and put it in one place, and then me and Martin called it microservices. So that's where microservices came from. It was very much standing on the shoulders of giants. But the interesting thing is microservices led to a massive explosion in innovation, actually. So if you think about all the observability tools, or many of the observability tools we've got now, things like just login frameworks, things like chaos engineering, all this stuff sort of exploded after microservices. You can start to see these this massive increase in items on our technology radar related to microservices. After that, we had, for example, Docker. Now, Docker first appeared in 2014. I mean, obviously containerization has been around for a long, long time, but this is when people started to use it in anger. Kubernetes, which is now synonymous with essentially how we work, that first appeared about 2015 on our radar. After that, we had React. React is only that old. And that led to this huge, well, not just React, but this explosion in JavaScript libraries over the years. Just back in sort of 2010, 2011, we weren't really talking about JavaScript. In fact, we were talking about things like treating JavaScript as a first-class language. Writing tests for your JavaScript. That was like the state of the art at the time. And then, boom, all of a sudden, it's sort of at the world. We then had this idea of platform engineering teams. That turned up a bit later on, but around about 2017, and I put this cartoon up, Now everyone wants one of these things. And actually, the problem, and I had this conversation yesterday, actually the problem with platform engineering teams is that many organizations don't get the fact that it's the self-service nature of AWS, or the self-service nature of the cloud, that makes us go faster. So what we end up doing is, we'll implement a platform over the top of whichever cloud provider we're using, but our developers will still have to ask the platform team to get stuff done. Right? We've kind of just put an API over the old ops team, if you like, and called it a platform team. Okay, boss, we've implemented the DevOps. Yeah, we still can't get stuff done. After platform engineering teams, we then had, I guess, maybe the latest big thing that's happened is data mesh. Again, that came out of one of my colleagues in ThoughtWorks. Came from Zhamak Delgani, who has now started a company where she's consulting on data mesh. And then fast forwarding a little bit, suddenly we've got this huge explosion in machine learning, in generative AI, whether that's images or language models. This year we had a theme which was the meteoric rise of practical AI. So actually being able to do stuff with it, actually domain-specific large language models as opposed to stuff that's in the cloud that other people have built and trained. So much so that my colleague Martin, on his site, he paired with the head of tech in China, Hu Zhao, who has been using ChatGPT as essentially a pair. So he uses ChatGPT as a pair when he's writing code. And it's a really interesting article, actually, about prompt engineering and about how you can use prompt engineering to use ChatGPT. But it's not all brilliant, right? I mean, I'm not going to go into a doom and gloom thing about generative AI, but, you've got Kent Beck tweeting about, out of all of his skills, 90% of them have been made redundant with the rise of large language models and generative AI, but 10% of those skills have suddenly become worth a lot more. British Telecom in the UK announced last week before last, that they're expecting generative AI to impact to the tune of about 55,000 jobs. So, I mean, this is obviously where we are at the moment. It's kind of an interesting point in the industry. I've got to bring this in because I just love this. It's an interesting point in our industry. It's an inflection point, if you like. You might have heard of this, the technological singularity, how we're accelerating towards some infinitely fast pace of change. I like this graph here. This is from the Department of Transportation Federal Highway Administration in the US, and it charts the rise of the motor car in the US. It charts how quickly that took off. This kind of basically ended up being an S-curve. Not an S-curve, exponential growth. And I was at a conference where they had two futurologists, and they were discussing, the singularity and what might be the cause of the singularity, whether it would be general AI or something else. And one of the futurologists, he was like a real optimist. He was saying, look, the invention of the automobile, turned into this innovation, which meant that so many jobs were created. Right? It was an overall massive net plus for the human race. And the other guy, who was a bit more pessimistic about things, he pointed out that that's true, but not if you're a horse. Right? So as the rise of the automobile kind of arrived, the population of horses in the US massively declined. The number of jobs associated with that horses were doing disappeared, essentially. So there's a kind of, six of one, six of the other kind of thing going on here. Now, that's where we've sort of come from the last 10 years. This sort of, it constantly surprises me that if you talk about Kubernetes these days, Kubernetes is just how we do stuff, right? I mean, Kubernetes is synonymous with deployment, synonymous with running our systems these days. Docker, similarly, or other containers. But they've only been around 5, 6, 7 years. People entering the industry now who see these things and see them as just how we do stuff, like it's only been 6, 7 years that we've started doing things in this way. Which is super interesting for me. But it also means, I think, that we've come to a point in the history of software engineering, if you like, where we kind of know how to do stuff. In general, we kind of know how to do stuff. So this is an example from our internal sensible defaults on our projects. So we kind of know that if we do these things, we're going to get predictable outcomes, if you like, or more predictable outcomes, frequent and continuous integration, going back to continuous delivery, test-driven development, this has been around a long time, pairing and mob programming, building security in fast and verified automated builds, automated deployment pipelines, early and continuous integration, and then managing your quality and debt effectively, and then building for production ready. So getting into production as early as possible, not necessarily going live or serving live users, real customers, but actually building your software in a way that you can deploy it straight away into production. I like the idea of the walking skeleton, which I think was originally Alistair Cockburn, but I first heard about it in the brilliant book, Growing Object-Oriented Software Guided by Tests by Nat Price and Steve Freeman. And in that, they talk about the idea of building, when you start off, you build the thinnest slice through your stack that you can. Even if it's just like a hello world app, using all the stack that you're going to be using in the future in production. Build this thinner slice, and crucially, have a way of pushing that slice into production. Get into a production-like environment as early as possible. So these are our sensible defaults. I mean, I like to think about this as, I do a lot of things like, sort of assurance, technical assurance on our big programs and things these days. And I like to think of these as the things that I would expect to see on every project. Like all of our projects, the products that are being built should be doing these things. And if you're not, sometimes you can't, but if you're not, you should probably have a reason why. You should be able to explain why you're not doing this stuff, why you're not adopting these defaults. There's this sort of canon we've built up about how we work, about the stuff that's effective, the stuff that allows us to, in a controllable way, in a more predictable way, much like, I guess, other forms of engineering, get software through a series of activities, through our testing process, through our software development lifecycle, and into production. So continuous delivery, I would argue, is at the heart of that. So written back in, as I say, back in about 2010, 2011. Continuous delivery is about how we can automate, in an automated way, a set of patterns to allow us to automate it. Oh my God, I'm repeating automated a lot. In a way, it's about a set of patterns to get our software into production in a predictable way, essentially, whilst building quality in. The great book, I think, Building Microservices, Sam Newman, this is the second edition. This talks actually not just to building distributed systems, although clearly that's a big part of it. But it talks to a lot of the other concerns around microservices, right? A lot of the concerns around things like, what does production ready mean? Patterns that when you're in production, things like circuit breakers and bulkheads, reliability patterns, things like that. How you test software. There's a lot in this book. And then another colleague of mine, actually 4 colleagues of mine, wrote Building Evolutionary Architectures, which is about, if you saw Barry O'Reilly's talk yesterday, which is about kind of trying to understand how to think enough up front about building software that will allow change to happen to it, if you like. So, like having designs that you can implement and those designs being robust in the face of change. Well, Building Evolutionary Architectures is about what Mark Richards was talking about as well, which is how we can use fitness functions, how we can guide our software architectures over time in the way that we want them to evolve. So make them malleable, changeable, and so on. We've then got this book, which I think, for me, is one of the most important books that's ever been written about what we do, Principles of Product Development Flow by Donald Reinhartson. I'll be coming to some of the principles in this quite shortly, but this really is about the economics, why the way, for example, lean software development, why agile software development methods, the economic underpinnings of those and why they're successful, why they make more sense for more organizations than more traditional stage-gated processes like waterfall, for example. It's also incredibly dense, so if you get it, don't expect to just read through it in one go, because I think there's like 217 different principles in there. Then we've got Accelerate. So Accelerate, the book, is the collection, if you like, of research and the research methods that Dora and the State of DevOps reports published over the years. It's collected together in Accelerate, and it talks to things like how we can understand whether we're getting better as a team using things like the 4 key metrics. It talks to why a set of the practices that we've sort of assumed work, like distributed systems or decoupled software architectures, or things like servant leadership, or why empowering organizations are more effective than command and control organizations. A lot of that is summarized in this book, which is, for me, one of the most important things, again, that's been written, because it underpins, it's peer-reviewed, it's proper research, and it gives us like a North Star to say, yes, the stuff we're going to be doing definitely is going to work, because we've got research that shows it does. And then team topologies. I talked a bit about this, when was it? I've lost track of days, on Tuesday. Team topologies is another, I think, instant classic, because team topologies gives us a vocabulary to talk to each other about how to organize teams. But again, it's been built up on a body of knowledge over the last 2-3 decades about what works, right? Based on things like principles of product development flow, value stream aligned teams, like visualizing your system, breaking your teams up by using things like Conway's law and the inverse Conway maneuver. So we have this set of things, these sort of practices, this history where we've come to. We've got this set of sort of default engineering practices, if you like, and then we've got a set of these sort of approaches to what we do that seems to work in general. And we've also got a bunch of research now which sort of points to why it works. In the sense, principles of product development flow, that's about things like queuing theory and network theory. Accelerate is about the research that sort of points to why things like fast flow makes organizations more effective. And then team topologies, again, is about network theory, team design, why certain styles of organization are able to go faster. So we've got this kind of why it works. But are there sort of underpinning reasons behind this? I mentioned queuing theory, I mentioned network theory, and so on, and I think there are. I should incidentally point out that Dave Farley published this book recently, which is brilliant. There's often been this sort of question about whether we should be allowed to call ourselves engineers. And Dave very, very eloquently talks to the fact that we now have a set of practices, principles, techniques that are repeatable, that we can use every time to give us a process that will give us good results every time, which is essentially what engineers do, proper engineers. I remember being on Go to Chicago. There was a keynote from Dr. Anita Singupta, who was the principal investigator for the NASA Curiosity rover's landing thing. So it's like there's this crazy thing where it entered the Martian atmosphere as a capsule, and then it popped the top of the capsule and it had parachutes, and then there was like a retro rockets fired, and then it lowered a thing to the surface on ropes and then flew away. Pretty crazy stuff. Proper engineering, that is. And she was explaining all this, and she had some time for questions, and someone put their hand up and said, but what about redundancy? What about if something failed? What would you do? what redundancy had you built in? And she literally just laughed. And when she sort of recovered from laughing, she said, oh, no, we don't build redundancy in, because redundancy is weight, and weight kills space projects. Anytime you add more weight, you're spending lots more money getting something out of Earth's gravity well. No, she said, we like to rely on this little thing we like to call engineering. And everyone in the room went, all software people went, oh, yeah, maybe we could learn something from that. But this is Dave's point. Dave's sort of point is that we are at that point now. We do have a set of these practices. We do have a set of techniques that allow us, in a repeatable way, to get good outcomes. So I think we are. I think Dave's onto something with this. Now, a lot of the examples or the books I've been talking about and the technologies and techniques are about this idea of flow. So continuous delivery includes in the title the idea of continuously getting software through a process into production, through a build pipeline into production. But flow goes further than that. Flow goes much further upstream than that, right? My former MD used to talk about the process being soup to nuts, from the starter to the dessert, if you like. From concept to cash, whatever you want to call it. And concept starts somewhere up in business land, generally, or with product ownership, or wherever that is, and feeds through a process, a series of steps, where value is added. Essentially, we've got some idea, some great idea, that's just an idea. And then through a series of value-adding steps, eventually you get, hopefully, software or features in production. And we've built up a set of techniques over the years to help us understand what's going on, to help us visualize flow. I appreciate I'm going to be preaching to the converted, I'm sure, in a lot of these cases. But here are some examples. Moving on from this. So, one example that you're all probably familiar with, Kanban boards, right? That's just that's a tool to visualize the flow of work through our team system. But there are other tools we can use. Burn-up charts, they allow us to understand at what point in the future we might be done, or for a value of done. Things like cumulative flow diagrams. Now, these are where we start to get people going, I've never seen a cumulative flow diagram before. Cumulative flow diagrams are kind of interesting, because what they allow us to do is, it's kind of like a burn-up chart, but they allow us to understand how each stage in our process is operating, whether we've got things backing up in testing, whether we've got things backing up in analysis or whatever. And they also give you some really interesting information around things like how long it's going to take you to get something from development through into testing. This is an example from sort of a real project of a cumulative flow diagram that sort of helps us visualize flow, the flow of work through a system. And what you can see here, the different colors of the different stages in our software development lifecycle, which is sort of up there, if that laser's visible. And what you can see is the individual little blocks of color. They show basically work that's waiting to move on to the next stage. And this allows us to visualize, to understand at what point in our process we've got blockages and so on. Super interesting. The next sort of visualization technique for flow we use, we actually had this on the radar recently because we thought like surely everyone knows about value stream mapping. Well, everyone does value stream mapping in their organization. Everyone takes the time to sit down and go, right, how does work flow through our software process? But it turns out many organizations don't do this. Many teams haven't come across these sort of tools yet, which is good for me as a consultant, because I can turn up and wow everyone with my toolbox with this in it. But I think, if more of us were able to take a step back and understand, visualize the system of work in which we're in, we'd be able to better optimize it. So value stream maps essentially what you see, you've got the sawtooth or the battlements or whatever, and the top bits, that's the length of time it takes to perform a particular activity, and we call that cycle time, or value creating time. We've then got the dips, that's how long between process steps we have to wait for stuff to happen. So for example, if the first activity is, say software development, like writing code, and it took us 3 days to write some code, then you've got that code sitting there for 10 days not doing anything. It's then picked up by a QA, and a QA spends a day and a half testing it. It then sits for 30 days waiting for the next release train, which is once a month in this case, before getting into production. And that's what we call lead time. Production lead time is from the beginning to the end of that process. And actually what we can see in this, and this is from a real team, what we can see in this is the amount of time actually spent doing real work is actually relatively small. The amount of time that the stuff, the code, the ideas, or whatever it is, sits waiting for something to happen to it is vastly greater, right? And you see this on many teams, where the actual value-adding steps, the writing code, the testing, the analysis is a short period of time, but then that thing that's been worked on sits in a queue somewhere for months often. I'm sure there are people in the room who've got Jira backlogs with stuff on them from like 5 years ago because it's so low priority it never gets actually done. Well, the lead time for that thing from 5 years ago, that's quite a long lead time, right? And that's why these are interesting, like to be able to visualize these things, to visualize how work flows through the system. But why does all this stuff work? So, again, if you were at Barry O'Reilly's talk yesterday, he talked a lot about complexity science, as did I on Tuesday. But this is related to complexity science. This is this idea of generative science. So Barry was talking about simulations and how you can use simulations to model the world, essentially, and to model software architectures. Now, those simulations are a form of generative science. NASA uses generative science as part of that, we do real engineering thing, right? So, when they do simulations in software of the rover or the spacecraft landing, or when they do simulations where they build scale models and drive them around, that's the engineering NASA do to de-risk things. It's a type of generative science, these sort of simulations. Now, I've got turtles in this. I like this bit. I'm not sure if anyone has ever written any logo code or ever taught anyone to write code using logo. It's a kind of classic language for teaching children how to write code. You have something called a turtle, and then you have commands that allow the turtle to move the turtle around. It's, oh my God, I can make it go forward, and I can make it turn around and go left. But actually, an evolution of logo called NetLogo has turned into one of the most powerful tools for studying complexity. So this is a simulation in NetLogo of birds flocking. So you've got a load of these little agents. This is an agent-based model. And there's a number of parameters you can set, the distance that they stay apart from one another, how quickly these agents can turn in circle and so on. And then you can run this simulation and see what happens. See what these sort of birds do. And depending on the set of parameters that you put in, really simple sets of parameters, you can simulate or not flocking behavior. So for this set of parameters, we don't get flocking. But if we change those parameters ever so slightly, we get this really complex behavior starting to emerge. Essentially what Barry O'Reilly was talking about yesterday in terms of attractors and things, that's what these are. And at a certain point, you achieve a sort of critical threshold where these agents, rather than wandering around randomly, they'll suddenly start this flocking behavior, which is kind of fun. I mean, there's another example here. So this is an example of virus spread. And obviously, this is quite simplistic. As the agents get closer to one another, there's a probability of them infecting a nearby agent and so on. It's quite simplistic, but actually this was used during the COVID pandemic. Not this model, clearly, because this is pretty simple. But agent-based models were used to simulate the spread of COVID. So when we had rules like, you stay within 2 meters, don't get within 2 meters of people, that was down to simulations being run using software very similar to this, where you could sort of model the current spread of the disease, and then you could say, okay, well, what happens if we tune this little parameter and stop people getting close to one another? Oh, well, the spread of it goes down. Maybe let's have that as a rule. This is actually some of my colleagues in India wrote this paper it's a tool called EpiRust, which was developed along with another tool, BharatSim, to do COVID, pandemic predictions, if you like, to simulate the spread of the disease in India. And it's written in Rust because you want to be able to simulate tens and tens of millions of people because it's India. They're kind of super interesting, how these agent-based models, these simple models, are able to actually simulate the real world to quite high fidelity, statistically, right? Statistically. Not exactly, but statistically. This is my favorite thing, or one of my favorite things. Agent-based models proved, essentially, that trickle-down economics doesn't work. So using an agent-based model, a bunch of complexity economists basically built a model where these agents exchange value. They all started off with equal amounts of value, and they would over time randomly exchange value with one another. And they found every time they ran the simulation that at the end of the simulation, you'd have one agent with all the value, and all the rest of the agents with none of the value. That's kind of fun. You can actually prove that or show that in a simulation. And they also showed that by implementing the different types of market controls in the simulation, that they could get the Gini coefficients for all these countries out, so the ratio between rich and poor. Essentially, they've kind of showed that oligarchy is the natural order of affairs unless things are controlled. Using simulations, right? Super interesting. But there's another type of, sort of science at play, or sort of discipline at play here. I'm sure we've all remember queuing theory from computer science. But that's what the principles of product development flow is all about. It's all about queuing theory and network theory. So this is a more complicated value stream map, if you like. So this is from another real organization. I showed this on Tuesday as well. And we've got an idea happening over here, and it goes through all the way into production over there. And in the middle, we've got this little blue thing here. That's code being written. It's just that little bit. There's some testing happening as well. This is my favorite bit, though. This bit with these circles here. This is two different types of integration architect who've each got their own canonical model, data model, and they're just updating each other's canonical data model in a circle. I'm not entirely sure why. You could literally take that whole thing out and the entire process would be kind of unchanged. But this is what a typical value stream map for a big, gnarly, old organization might look like. There's a number of interesting features in this value stream map, right? So this over here, all of this is sort of post-development. This is a bunch of system integration testing, regression testing, performance testing, blah, 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 blah. Right? And what's happening is, a piece of work basically gets finished in development, and then it goes and sits and waits to be system integration tested for a month, and then it waits to be regression tested for a month, and so on and so on and so on. And what these value stream maps allow us to do is reason in interesting ways about the flow of work through them. So here's a principle from Principles of Product Development Flow, the batch size queuing principle. Reducing batch size reduces cycle time. This is at the heart of why continuous delivery works. This is the reason continuous delivery works. Reducing batch size reduces cycle time. What do we mean by batch size? Well, say you've got a project that you want to build. A traditional waterfall process would be we do all the analysis, we'll do all the software architecture and design, then we'll do all the development, then we'll do all the testing, then we'll do all the deployment. We'll deploy everything at once. And that would be a 100% batch, all the requirements moving in 100% batches through your software development lifecycle. As opposed to agile or lean software development processes, where what we want to do is take one item, and as soon as it's been analyzed, we want to start development. As soon as it's been developed, we want to test it. As soon as it's been tested, we want to deploy it, so it starts earning money. And that would be single piece flow, or the minimum batch size. Essentially what this queuing principle says is, anytime you reduce batch size, you reduce cycle time, which means reducing batch size leads to you going faster, improving throughput. Just breaking work up into smaller chunks means you go faster, because it's math. Have a look at this, right? So this is a cumulative flow diagram, and this shows you two different batches going through into production. So we've got the first batch gets deployed essentially, just above the I in time. I should put a t equals 0 on that. And then we've got another batch afterwards. And so all of these, essentially, you don't start earning money on these batches until they're in production. And so you don't start earning money on all that stuff on this side until halfway through that process. Whereas with continuous delivery, just by breaking those batches up into smaller batches, you get the same amount of work, but deployed much more frequently. You suddenly start earning value here rather than here. And I'll give you a demonstration of that in a bit. In fact, Don goes on to say, batch size reduction can enable us to shorten cycle time, often by an order of magnitude, without changing capacity utilization. Essentially, if you deploy twice as frequently, if you break this stuff up into half its size and then deploy half, you've doubled your throughput as a team. It's the easiest way. If someone says to me, can this team double their throughput? You go, yes, break stuff in half, that's it, you've doubled throughput. In this book, Principles of Product Development Flow, Don talks about the properties of large batches sitting in queues. Work sitting in queues in our processes, in these software development processes, they lead to longer cycle times, increased risk, more variability, essentially. Queues are the kind of enemy. Is another principle, the principle of congestion collapse. Martin Fowler talked about this recently. When loading becomes too high, we see a sudden and catastrophic drop in output. Basically, if you've got too much going on, too many projects happening at once, essentially what you end up with is everyone working really, really hard, but going really, really slowly. Because what happens is the system undergoes what's called a congestion collapse. You can see that congestion collapse. This is a NetLogo simulation of a motorway, essentially, an interstate or whatever. And in this simulation, this is a congestion collapse. When someone brakes in front of you in a car, and you have to brake, and then the car behind you brakes and brakes and brakes, and you end up with this bunching phenomenon, where eventually everyone comes to a stop, and then has to start again. That's because of congestion collapse. It's purely because you've got too many cars on the motorway for a given speed. There's another principle, control occupancy to sustain high throughput. So the way you make people go faster on a motorway is to stop having so many cars. If you have fewer cars, you don't end up with the same behavior. You don't end up with these congestion collapses. You just have this continuous flow. This is what happens when we talk about like having slack in our system. Not being 100% utilized, working at sort of 70, 80% utilization. With that sort of slack in the system, you don't undergo, as a team, this sort of phenomenon where everything is just like, you have this congestion collapse phenomenon. There's another queue size control principle. Don't control cycle time, control queue size. Now, you had lunch today. Were there queues? I'm going to pick on someone. There were queues. Would there have been a longer queue if there was just a single place to get lunch? Yeah. And if there were like 100 places to get lunch, the queues would be shorter, right? Yeah. This is an interesting thing because everyone who goes to conferences understands about conference lunches, right? So the interesting thing with this idea of controlling queue size is this is what conferences try and do when they have more than one lunch station. Or if you've been to NDC or Java Zone, they have continuous food delivery all day, right? Because they want to try and make people get their food as fast as possible. So if you've got, essentially, lunch served at 1 o'clock, and then essentially you've got a bunch of hungry people suddenly finish a talk and arrive at lunch, suddenly the queue size jumps up in front of the lunch stations, right? So I was there before, because I wasn't in the previous talk. I got my lunch really quickly. I'm one of these lucky people down here, but if you were later, you were standing in a queue. Now, the problem with lunch is it's served at a constant rate, so the departures from the queue, essentially, are constant. And that's what leads to this big jump in queue depth here. Now, if you measure how long it takes you from the back of the queue to eating your lunch, that'll give you one estimate, right, of how long of throughput, or how long things are going to take. In this case, you'd measure, 1 minute 35 or whatever it is, or 35 minutes or whatever. And you wouldn't know it was taking that long until 1:30. But if you just measure the queue depth, how many people are waiting in front, you immediately get to understand the load on the system and how long things are going to take, what the cycle time is. Essentially, by understanding the stuff that's waiting to be done, how much stuff is in a queue in front of a stage of work, you can understand what the cycle time is. And this is basically a law called Little's Law. Now, these are just some of the things I've been some of the curiosities I've been pondering over the years, which brings me to how work works. Excuse me. We've got all these techniques, practices. We've sort of settled in this kind of, I guess, methodology and approach to how we can build software. We've got a bunch of theory behind things like queuing theory, about how to organize our teams, how to optimize for fast flow, a bunch of tools to visualize that kind of stuff. So I was wondering, is there something underneath that? And I think there might be something kind of interesting. Now, can we simulate the real world? Talking about generative science, wouldn't it be interesting if we could actually simulate us, like how we work in companies? Like the teams that we're in, we could push a button and say, okay, now ThoughtWorks works like X, and see it. See the teams producing software, see the teams learning, see people acquiring skills and all that kind of stuff. I think that would be super interesting. And I think using a combination of these techniques, I think we can actually start to simulate the real world in software and come up with interesting results that we can ask questions of. Now, I know you think this might be mad, but Google published this paper recently, Generative Agents, Interactive Simulacra of Human Behavior, Google Research in conjunction with Stanford. They've got a model, an agent-based model that they run. You can go and play with it online. It looks like this, nice 16-bit art, game art and things. Essentially, you've got a bunch of these agents. They just go around living their lives, doing stuff, going to work, visiting shops, that kind of thing. And they interact, interestingly, with Google stuff. They interact via, is it Bard? Can't remember, but via a large language model. So they actually talk to one another using, like this large language models talking to one another, essentially, in these agents, right? And what they found is these agents do things like self-organize. So if one of them decides every now and again to have a party, because they talk to one another using a large language model, suddenly everyone in the community knows that there's a party, and they'll all turn up at a party. They'll self-organize to go to work. They teach each other new behaviors. Some of them even fell in love. Simulating the real world using generative science. This is an example of the stuff that Aisha Khan is doing at the moment, waking up and completing her morning routine. But what good is that to us? Modeling a bunch of people in what is actually a Dungeons and Dragons world. Well, I think we can take similar stuff. In fact, this is what I've been working on for a number of years. Similar ideas, agent-based models, generative science, complex adaptive systems, and so on, and start to model what we do and come up with interesting results. So, you can take these value streams and start asking, what does this stuff really mean? Right, we've got coordination of work happening. We've got scheduling of work happening. We've got queues of work in here. We've got different roles that are represented. Enterprise architects. Enterprise architects do different things. They create solutions or they design bits of software, whatever it is they do. When you start to understand what we do like that, or think about what we do like that, as I say, you've got these different roles in here, then you can start to build up an agent-based model based on what we do. Based on writing code, based on testing software, based on committing software into repositories and so on. So in this case, I've got an enterprise architect machine. If there are any EAs in here, sorry. Enterprise architect machine, and they do a number of stuff. They've got an inbox, and a bunch of stuff turns up in their inbox, and they process it, and they put it into their outbox. They process it, put it into their outbox. And by simulating people as these sort of by using agents to represent people on teams, we can come up with some interesting things. So how you do that, the details of that, talk to me afterwards. I'm a massive nerd on this stuff. This is something called a behavior tree. So behavior trees are essentially a finite state machine in graph form. And what the behavior tree does is allows you to put in a set of behaviors, what people do on a day-to-day basis. So, as a developer, I might, my general thing is writing code, but, I might need to go to the bathroom every now and again. I might need to, ask my boss a question or ask my tech lead a question. All of these behaviors can be put into a behavior tree. This is how computer games work. You can then write some C#, in this case C#, to implement these behavior trees. And when you run these behavior trees on lots, when you run these agent-based models using these behaviors, you get emergent behavior because they're complex adaptive systems. You put some variance in there, and suddenly interesting things start to happen. You can start to simulate the world of work. And this is a very early version of the prototype I've been building in Devoxx, which shows two different types of teams writing, basically, two different types of teams and how they're working, essentially, to develop software. And in fact, those two different types of teams, one's a waterfall team and one's a lean team. By which I mean one is transferring 100% batches, everything is analyzed, everything is developed, everything is tested. And the other team is doing single-piece flow. So as soon as a piece of work is ready to be done, and I'm a developer, I can do that work, I'll pick it up and I'll do it. And what we see, essentially, in the simulation is the difference between value delivered, essentially 4 key metrics, between the two different types of model, waterfall versus agile. And so the red line is showing the cumulative value for the agile team, and the blue line is showing the cumulative value over time for the waterfall team. Similarly, you've got the average lead times for both. So using generative science, using some of these ideas from queuing theory, from information theory and so on, we can put all that, and using modern recent advances in terms of things like behavior trees and complex adaptive systems, we can put all that into simulation. And actually, we can simulate how the world works. We can simulate how we work. And my dream with this is to turn it into a tool we can actually use to make changes in simulated form rather than in the real world and see if they work or not. So I mentioned all this stuff that we do that seems to work. I mentioned the stuff is how it works. And then I think there's some principles underlying this, which is complexity science, which is things like network theory and so on. And that's why it works. There's a bunch of books here. I'm slightly over time, so apologies. Thank you very much for seeing my work in progress. Thanks.